In the late 1990s, two teams of astronomers were trying to measure how fast the universe was slowing down. That was the expectation. Gravity should be pulling everything inward, gradually reducing the speed of cosmic expansion that began with the Big Bang. The universe, after all, is filled with matter, and matter attracts. But when those astronomers looked deep into the sky, they saw something that didn't make sense. The expansion wasn't slowing down at all. It was speeding up. This discovery would change modern cosmology forever. To understand how shocking it was, picture the universe as a ball thrown upward. Everyone expected it to rise, slow, and eventually fall. Instead, it began to accelerate upward, faster and faster, as if an invisible hand were pushing it away. That invisible push was given a name: dark energy, a force that seems to counteract gravity and drive galaxies apart. But what exactly is this energy? And why did we only discover it recently, billions of years after the universe began? The answers lie in how astronomers learned to measure distance across the cosmos. They used objects called Type 1a supernovae, dying stars that explode with nearly uniform brightness. Because their true brightness is known, scientists can compare how bright they appear from Earth to estimate their distance. Fainter means farther away. By combining those distances with the galaxy's redshifts, the stretching of light due to cosmic expansion, scientists can calculate how fast the universe has been growing over time. When those measurements were plotted, the pattern was unmistakable. Distant galaxies were moving away faster than closer ones, and the rate of acceleration was increasing. Something unseen, some form of energy embedded in the very fabric of space, was pushing everything apart. This wasn't the first time such an idea had appeared. Back in 1917, Albert Einstein added a cosmological constant to his equations of general relativity to keep the universe static, believing it neither expanded nor contracted. When evidence later showed the universe was indeed expanding, Einstein called that constant his greatest blunder. But decades later, it suddenly made sense again. A constant energy pervading empty space could be the missing ingredient behind cosmic acceleration. The implication was staggering. Roughly 70% of the universe seemed to consist of this dark energy. All the stars, planets, gas, and galaxies, everything we can see, make up less than 5%. The rest is dark matter, and this mysterious energy that defies direct detection. We don't see it, we don't touch it, yet it dictates the fate of everything. Today, every major cosmological model includes dark energy as a fundamental component, yet its true nature remains unknown. It could be a property of space itself, a vacuum energy that never fades, or a dynamic field that evolves with time. Whichever it is, the story of dark energy begins with the simple act of looking farther than anyone had before and realizing the universe had a secret. Once astronomers realized the universe was accelerating, the next question was, how fast and why? Measuring motion on a cosmic scale is not like tracking a car's speed or a planet's orbit. The universe itself is expanding, space stretches, and with it, every beam of light we receive. To study this motion, astronomers measure a quantity called redshift. When light travels through expanding space, its wavelength lengthens, shifting toward the red end of the spectrum. The greater the redshift, the farther that light has traveled, and the earlier in cosmic history it was emitted. But to transform redshift into distance, scientists need what's known as a cosmic yardstick, something whose intrinsic brightness or size is already known. Type Ia supernovae are one of these, but they're rare and fleeting. So astronomers turn to other tools: galaxies themselves, patterns in the cosmic microwave background, and baryon acoustic oscillations, subtle ripples in the distribution of galaxies that echo the sound waves of the early universe. Each of these serves as a different rung on the cosmic distance ladder. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. It is the oldest light we can see, released when the universe was just 380,000 years old. By mapping tiny temperature fluctuations in this background, missions like COBE, WMAP, and Planck revealed the universe's overall shape, age, and composition. The results confirmed that roughly 70% of the universe's energy budget is dark energy. These measurements, cross-checked against supernova data, showed remarkable agreement. The universe wasn't just expanding, it was doing so faster with time. Still, redshift is not the same as speed in the traditional sense. Galaxies aren't moving through space away from us. Rather, space itself is stretching. Imagine raisins in a rising loaf of bread. As the dough expands, the raisins move apart, even though they remain stationary in their own local pockets. Each galaxy experiences the same phenomenon, seeing every other galaxy move away in all directions. There is no true center, only expansion everywhere at once. To track this stretching with greater precision, astronomers rely on massive surveys that capture millions of galaxies at different distances. The Sloan Digital Sky Survey, for instance, mapped the positions and redshifts of over 1 million galaxies, creating a three-dimensional view of cosmic structure. The newer Dark Energy Survey and Dark Energy Spectroscopic Instrument, or DESI, are now extending that map billions of light-years deeper. DESI alone can measure redshifts for up to 40 million galaxies using 5,000 robotic fibers that feed into its spectrograph, a technological marvel that turns the sky into a cosmic speedometer. With these instruments, scientists aren't just charting where galaxies are, they're revealing how the expansion rate has changed over billions of years. The pattern that emerges acts like a fingerprint for dark energy. If that fingerprint drifts or bends over time, it could mean dark energy isn't constant, that it evolves, waxing or waning as the universe ages. This quest for precision has exposed one of modern astronomy's great puzzles. Different measurement methods give slightly different answers for how fast the universe is expanding right now, a disagreement known as the Hubble tension. Local measurements using nearby galaxies suggest one number, while observations of the distant cosmos imply another. Whether this is an error in data or a clue to new physics remains one of the most intriguing questions in cosmology today. Before dark energy became a household term in cosmology, it began as a quiet anomaly buried in supernova data. In 1998, two research groups, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how much the universe's expansion had slowed since the Big Bang. They assumed gravity would eventually win the cosmic tug-of-war, causing expansion to decelerate. But when they examined distant Type 1 supernovae, the results were startling. These supernovae appeared dimmer than they should have been if the universe were simply coasting or slowing down. The only way to explain their faintness was if those galaxies were farther away than expected, meaning the universe's expansion had actually accelerated over time. What had begun as a calibration test became the discovery of a phenomenon no one had predicted. Type 1 supernovae are ideal cosmic yardsticks because of how they form. They occur when a white dwarf star, the dense remnant of a medium-sized star, steals matter from a nearby companion until it reaches a critical mass. At that point, carbon and oxygen inside ignite in a runaway thermonuclear explosion, releasing an enormous burst of light. Every event shines with nearly the same intrinsic brightness, allowing astronomers to compare apparent brightness to determine distance with extraordinary accuracy. When dozens of these explosions were plotted against their redshifts, the curve of cosmic expansion bent in the opposite direction from what theory predicted. The further back in time scientists looked, the slower the expansion had been, and more recently, it was speeding up. That single reversal in the curve was the fingerprint of dark energy. To be sure, astronomers rechecked everything. They examined dust interference, calibration methods, and the possibility that supernovae might have changed over time. But the pattern held. No matter how the data were sliced, the acceleration persisted. Independent teams confirmed it using galaxy surveys, the cosmic microwave background, and gravitational lensing, all converging on the same conclusion. The discovery was so profound that it earned the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. Yet even as the world celebrated, the scientists themselves admitted they didn't truly understand what they had found. The force driving the acceleration could not be measured directly. It left no trails, emitted no light, and produced no detectable particles. It was everywhere and nowhere at once. This wasn't just another cosmic curiosity. It reshaped the timeline of everything. If dark energy exists, and all evidence points to it, then the universe will never stop expanding. Galaxies will drift apart faster and faster, stars will burn out, and cosmic horizons will fade beyond view. What began as a subtle dimming in a few ancient supernovae now defines the long-term fate of the cosmos. That realization led scientists to revisit one of Einstein's most controversial ideas, his cosmological constant, a concept once dismissed as unnecessary but suddenly resurrected by the new evidence. Could the old constant, reinterpreted, be the mathematical key to dark energy? The revelation of an accelerating universe forced scientists to rewrite decades of cosmological thinking. Before 1998, the reigning debate wasn't about acceleration at all. It was about whether gravity would eventually stop expansion or let it continue forever. The two primary models of the universe were the closed universe and the open universe. A closed universe would have enough mass and gravity to halt expansion, leading to a future collapse called the Big Crunch. An open universe with too little matter to stop the momentum would expand endlessly but at a slowing pace. The supernova data ruled out both scenarios. The universe wasn't slowing down, it was racing ahead faster every day. This demanded a new model altogether, one where gravity alone couldn't explain the behavior of space-time. Something else had to be acting on a cosmic scale, something that wasn't matter, wasn't radiation, but still carried energy. In Einstein's equations of general relativity, energy and matter shape the geometry of space-time itself. Add more mass, and the cosmic fabric curves inward. Add more energy, and it can curve outward. When astronomers reintroduced the cosmological constant, the lambda term Einstein had once discarded, it fit perfectly into this new picture. This constant represented a uniform energy density filling all of space, one that doesn't thin out as the universe expands. It was a mathematical representation of dark energy. However, labeling dark energy as simply Einstein's constant didn't end the mystery, it deepened it. If it were truly constant, quantum physics predicts the vacuum energy of empty space should be enormous, at least 10 to the 120 times greater than what observations show. This staggering mismatch, known as the cosmological constant problem, remains one of the greatest unsolved issues in physics. It's as if nature fine-tuned the universe to expand at precisely the rate needed for galaxies, stars, and life to exist. No faster, no slower. As new observations poured in, old models crumbled further. The lambda CDM model, short for lambda cold dark matter, became the new standard. In it, lambda stands for dark energy, CDM for dark matter, and together they describe a universe composed mostly of invisible ingredients. About 68% dark energy, 27% dark matter, and only 5% ordinary matter. Everything we can touch, see, or measure directly. This model explains nearly all large-scale observations, from the cosmic microwave background to galaxy clustering. Yet its success comes with an uncomfortable truth. We understand the smallest portion of the universe best, and the largest portion barely at all. Dark energy and dark matter dominate the cosmic balance sheet, but their true nature remains hidden behind equations and indirect measurements. Still, the power of the lambda CDM model lies in its precision. It matches the observed expansion history and predicts the evolution of structure in the universe remarkably well. Every new telescope test, from Hubble's deep fields to Planck's all-sky maps, has reinforced it. But the more accurate our measurements become, the clearer the discrepancies appear. The Hubble tension, for example, might be a whisper that the model, while elegant, is incomplete. For now, dark energy acts as the invisible thread holding this model together. It may yet turn out to be more complex, a dynamic field, or something even stranger than Einstein imagined. To find out, scientists must measure not only how much the universe expands, but how that expansion changes with time. If dark energy were truly constant, the story might end there. But the universe rarely cooperates with simple answers. The cosmological constant works beautifully on paper, yet mounting evidence hints that the acceleration of space might not be perfectly steady. Something subtle, something alive within the equations, could be changing with time. To test this, cosmologists introduced models of dynamic dark energy, treating it not as a fixed value, but as a field that evolves as the universe ages. One of the most studied examples is called quintessence, a term borrowed from ancient philosophy meaning the fifth element. Unlike a constant energy density, quintessence can strengthen or weaken depending on how the universe expands. Imagine a kind of cosmic tide that ebbs and flows, sometimes driving expansion more forcefully, other times relaxing its grip. These models make specific predictions. If dark energy changes over time, it would subtly alter the pattern of cosmic expansion. Galaxies would form differently, and the growth of cosmic structures, clusters, filaments, and voids would carry a slightly different imprint than what a constant dark energy would produce. Astronomers hunt for these fingerprints by comparing how the universe looked billions of years ago to how it looks today. That's where massive surveys like Euclid and the Nancy Grace Roman Space Telescope come in. Euclid, launched by the European Space Agency, is mapping the geometry of the cosmos with unprecedented precision, measuring how galaxies are distributed in 3 dimensions. Roman, NASA's next flagship observatory, will do the same using wide-field infrared imaging, peering deep into cosmic history. Together, they will track how dark energy has sculpted the universe from its early youth to its accelerating present. But what could a dynamic dark energy field actually be? Some physicists describe it as a new form of scalar energy, a smooth, diffuse field similar in spirit to the one thought to have driven cosmic inflation shortly after the Big Bang. In this view, dark energy might be the lingering echo of that inflationary force, now operating on vastly lower energy scales. Others suggest it could stem from modified gravity, meaning Einstein's equations themselves might need adjusting at cosmic distances. These aren't wild speculations. They're frameworks built to be tested. If dark energy truly evolves, its effect on expansion would shift the balance between matter and energy in measurable ways. Light from distant galaxies would show a slightly different pattern of redshifts, and gravitational lensing, the bending of light by mass, would reveal subtle deviations in how structure grows. Already, hints are emerging. Some studies of galaxy clusters and cosmic microwave background maps suggest a possible tension, an acceleration rate that may be slightly higher or lower depending on which cosmic era you observe. While these signals are far from conclusive, they keep theorists awake at night. If confirmed, a time-varying dark energy would revolutionize physics. It would mean the vacuum itself is not stable but dynamic, evolving alongside the universe. The laws of nature, once thought constant, might be part of a grander, shifting landscape. For scientists, that possibility is both thrilling and unsettling, because it means the universe we measure today might not be governed by the exact same rules tomorrow. The universe is an endless tug-of-war between two invisible forces, gravity pulling inward and dark energy pushing outward. Every star, planet, and galaxy exists within this fragile equilibrium, a balance so delicate that even the slightest shift could have rewritten cosmic history. Gravity, as Einstein described it, isn't a force in the traditional sense. It's the curvature of space-time caused by mass and energy. The more matter you pack into a region, the deeper the curvature becomes. Galaxies cluster, stars orbit, and light bends, all guided by this invisible geometry. For billions of years after the Big Bang, gravity was the architect of structure, drawing hydrogen into the first stars and galaxies, weaving the cosmic web that defines the universe we see today. But as the universe expanded and matter spread thinner, gravity's influence weakened. That's when dark energy began to dominate. It doesn't attract or clump like matter. It acts uniformly everywhere, stretching the fabric of space itself. The more space there is, the more dark energy exists, creating a feedback loop that accelerates expansion further. Think of gravity and dark energy as competing artists shaping the same canvas. Gravity paints detail, gathering matter into galaxies and stars, while dark energy stretches the canvas wider with every passing moment. For most of cosmic history, gravity had the upper hand. Then, about 5 billion years ago, the scales tipped. The universe's density fell below the critical threshold, and dark energy's outward push overtook gravity's inward pull. Since then, cosmic expansion hasn't just continued, it has accelerated relentlessly. The battle isn't uniform. On smaller scales, like inside galaxies or galaxy clusters, gravity still dominates completely. The Milky Way's stars will remain bound together even as distant galaxies race away. But on the largest scales, across billions of light years, dark energy wins effortlessly. It dictates the fate of galaxy clusters, voids, and the cosmic web itself. This balance is so finely tuned that physicists can express it through the critical density, the precise amount of matter and energy needed for the universe to hover between eternal expansion and eventual collapse. Observations show we're astonishingly close to that value, yet just far enough on the lighter side for dark energy to prevail. If gravity represents the universe's desire to gather, dark energy represents its instinct to expand. Together they define the cosmic rhythm, one slowing, the other accelerating, both inseparable from the structure of space-time itself. Without dark energy, galaxies would have long ago begun to coalesce, and the night sky would grow brighter as cosmic structures crowded closer. Without gravity, stars and galaxies could never have formed at all. The fact that these two immense, opposite forces balance so precisely is one of modern science's most puzzling coincidences. Why should their magnitudes be so perfectly matched at this particular moment in cosmic history? This question, known as the cosmic coincidence problem, has become one of the great philosophical riddles in cosmology. Some physicists speculate that it's simply a fluke, a temporary overlap in two evolving curves. Others wonder if it points to something deeper, perhaps a hidden link between gravity and dark energy that we have yet to uncover. If dark energy is the invisible hand accelerating the universe, then the Hubble constant is its signature, the number that tells us how fast space is expanding right now. Measuring it should be simple in theory. In practice, it has become one of the greatest scientific puzzles of our time. The Hubble constant links distance to velocity. The farther a galaxy is from us, the faster it appears to be receding. Edwin Hubble first noticed this pattern in 1929, revealing that the universe was expanding at all. But today, nearly a century later, scientists can't agree on the exact value. One method, using nearby Cepheid variable stars and type Ia supernovae, finds an expansion rate of about 73 kilometers per second per megaparsec. Another method, based on the cosmic microwave background observed by the Planck satellite, gives a slower rate of 67 kilometers per second per megaparsec. That 6-kilometer difference may not sound like much, but in cosmology, it's enormous, the kind of discrepancy that can't be explained by measurement error alone. Both methods are precise and independently confirmed, yet they refuse to converge. This conflict is known as the Hubble tension, and it has become one of the defining challenges for modern cosmology. There are two possible explanations. The first is that one or both measurements are somehow flawed, that unknown systematics in the data are skewing the results. The second, more exciting possibility is that the tension is real, a sign that our current understanding of the universe is incomplete. If so, dark energy itself might not behave as we assume. One idea is that the properties of dark energy changed between the early and late universe, stronger at first, weaker now, or perhaps the opposite. Such a shift could subtly alter the expansion history, reconciling both measurements. Another proposal involves early dark energy, a temporary phase of repulsive force that briefly acted just before the universe became transparent. This early burst could have left an imprint on the cosmic microwave background, changing the inferred expansion rate. The Hubble tension has become the testing ground for new physics. Researchers are exploring exotic models that tweak Einstein's equations or introduce new particles that slightly change how matter and radiation interacted in the early universe. So far, no single explanation fits perfectly, but each attempt pushes the boundaries of what we know. What makes this problem so fascinating is that it connects every scale of existence. Measuring the Hubble constant ties the flicker of a distant star to the shape of the universe itself. Each telescope, each recalibration is an act of rewriting cosmic history. For now, the tension remains unsolved, a quiet whisper that something about the cosmos still hides beyond our reach. The mystery deepens with every new observation, but one truth stands firm. The universe is expanding faster than gravity can explain, and that acceleration demands an answer. If the Hubble tension is the riddle, the next generation of observatories are the tools built to solve it. Over the coming decade, a fleet of telescopes, both in orbit and on Earth, will turn the entire sky into a laboratory for dark energy. Together, they aim to answer a question that's haunted cosmology since 1998. Is the universe's acceleration truly constant, or is it changing with time? At the forefront is the Nancy Grace Roman Space Telescope, NASA's flagship mission for the 2030s. Equipped with a massive wide-field infrared camera, Roman will image the sky with a resolution and scope that dwarf Hubble's view. Each snapshot will capture the light of hundreds of millions of galaxies, creating a three-dimensional map of the cosmos. By comparing how galaxies cluster at different distances, Roman will reveal how dark energy has influenced structure formation throughout history. Working in parallel, the Euclid mission from the European Space Agency is already scanning deep space, combining weak gravitational lensing and galaxy redshift surveys to trace how matter bends light. Every distortion in those measurements tells a story about the balance between gravity and expansion. Together, Euclid and Roman will give scientists the most precise measurements yet of how the universe's growth has changed across billions of years. On the ground, the Vera C. Rubin Observatory in Chile is preparing to revolutionize time-domain astronomy. Its legacy survey of space and time will capture the entire southern sky every few nights for a decade, identifying billions of transient events, supernovae, quasars, and variable galaxies, each one a probe of cosmic expansion. The Rubin telescope's enormous field of view will allow astronomers to measure how dark energy affects the universe's structure on vast scales and minute timescales simultaneously. Meanwhile, the James Webb Space Telescope continues to peer even deeper, not only at early galaxies, but also at type Ia supernovae and gravitational lenses that can independently test dark energy's effects. Webb's infrared vision complements these surveys perfectly, adding the fine detail that connects broad statistical maps to individual physical processes. Together, these instruments form a cosmic symphony, each telescope playing a different part of the same melody. Some map the geometry of the universe, others its composition or rate of change. When combined, their data will allow scientists to reconstruct the full expansion history of the cosmos with unprecedented precision. For the first time, humanity will have the tools to see dark energy's fingerprints across both time and space. If the acceleration changes, even slightly, these observatories will detect it. If it doesn't, they'll confirm once and for all whether the vacuum of space truly contains a constant energy density, or if something deeper is unfolding beneath the surface. Every measurement of dark energy points toward a single, unsettling truth. The universe's expansion isn't slowing, and it never will. What began as a gentle outward drift has become a runaway process written into the fabric of reality. The question now isn't whether the universe will end, but how. If dark energy remains constant, the universe will follow a path cosmologists call the Big Freeze. Over trillions of years, galaxies will drift so far apart that their light will never reach one another again. The night sky will empty, stars will exhaust their fuel, and new ones will no longer form. Black holes will slowly evaporate through Hawking radiation, leaving only a thin haze of particles in a dark, silent expanse. It's not an explosive ending. It's a gradual fading of everything we know into thermodynamic stillness. But if dark energy grows stronger with time, a possibility described by the phantom energy model, the outcome becomes far more dramatic. In that scenario, the universe could end in a big rip. Expansion would accelerate to the point that galaxy clusters, galaxies, solar systems, and eventually atoms themselves would be torn apart by the stretching of space-time. It's a vision of cosmic destruction that would occur tens of billions of years from now, yet its seeds are already being measured in the faint light of distant galaxies. Alternatively, if dark energy weakens or changes sign, gravity could eventually regain control. Expansion might slow and reverse, leading to a big crunch, a collapse of the universe back into a dense state, perhaps triggering another Big Bang. Some cosmologists even speculate about an oscillating universe, an endless sequence of expansions and contractions, each cycle birthing new cosmic structures from the ashes of the last. For now, the evidence leans strongly toward eternal expansion. Observations from the Planck satellite, supernova surveys, and baryon acoustic oscillations all indicate that dark energy behaves like a constant energy density, pushing the cosmos outward forever. The rate may change slightly, but the direction remains the same, toward isolation, entropy, and infinite cold. Yet even that distant outcome carries a strange beauty. In the Big Freeze, time doesn't end suddenly. It stretches endlessly, like a river flowing slower and slower until motion itself becomes imperceptible. Future civilizations, if any survive that long, would see their local stars fade and galaxies vanish, yet their physics would remain the same. The laws of nature, forged in the first moments after the Big Bang, would continue to operate even as the universe drifts into silence. And still, dark energy leaves room for wonder. Could it decay into something else? Could it trigger new physics, perhaps even a rebirth of the cosmos under different conditions? The universe has reinvented itself before, through inflation, through recombination, through the emergence of structure from chaos. Perhaps dark energy is simply the next chapter, an unfinished sentence in the universe's story that we've only just begun to read. In every era of science, humanity has stumbled upon something so vast, so counterintuitive, that it forces us to rethink our place in the cosmos. Dark energy is that discovery for our age. It reminds us that the universe is not just expanding outward, it's expanding in meaning. When we first learned that the Earth orbited the Sun, it shifted the center of our world. When we learned that the Milky Way was one galaxy among billions, it humbled our scale. But when we discovered that invisible energy dominates everything, dictating the past, present, and future of the cosmos, it redefined what everything even means. We live in a universe where the most powerful influence is something we can't touch, see, or measure directly, and yet its signature is everywhere. Dark energy teaches us that the universe is not static. It is a living, evolving system still unfolding 13.8 billion years after its birth. It tells us that space itself is not empty. It hums with unseen energy that bends, stretches, and sculpts reality. It invites us to imagine what it means to exist in a cosmos where emptiness is not nothingness, but a dynamic sea shaping the fate of all things. The search for dark energy has already changed how we do science. It has united cosmology, quantum physics, and philosophy into a single pursuit to understand not just what the universe is, but why it behaves the way it does. Each new telescope and every recalibration brings us closer, even as the answers raise deeper questions. What if dark energy is connected to quantum fluctuations of the vacuum? What if its origin lies beyond our universe, a consequence of higher dimensional space or multiversal physics? Every possibility expands our imagination as much as our equations, and maybe that's the true legacy of this discovery. Dark energy is not just a mystery to solve, it's a mirror reflecting our own curiosity. It shows that human beings, born on a small blue planet orbiting an ordinary star, have developed the tools to measure forces acting across the entire universe. We are the first species known to look into the void and realize that the void itself has power. The more we learn, the more humbling the picture becomes. Our galaxies, our atoms, even our thoughts, all unfolding within a cosmic story written mostly in invisible ink. Yet that ink, that unseen energy, has guided the universe from the first flicker of starlight to this very moment. It will continue long after the last photon fades. The mystery of dark energy endures not because it hides, but because it reveals how much more there is to understand. Perhaps the universe isn't racing away from us. Perhaps it's inviting us to chase it, to keep asking questions, to never stop reaching for the horizon that keeps moving just out of sight. And as long as we do, the story of discovery continues. Because in the end, the real force expanding the universe faster than expected is curiosity itself.